in 1907, 2 years after the miracle year, Einstein had been asked to write a review article on the special theory of relativity for a science yearbook. It was really designed not for the general public necessarily, but for other scientists, just summarizing some of the key results of previous years. And he wrote later, reminisced later, that he had what he called the happiest thought or most fortunate thought of his life. In fact, here's how he described the situation. He had been bothered, as he thought more about the special theory of relativity, he was bothered by a couple things. And one thing was there's only constant velocity of motion, and therefore it wasn't general enough, and also didn't take into account any gravitational effects. So he had been mulling those things over. And later he reminisced that I was sitting in a chair in the patent office in Bern, Switzerland, when all of a sudden a thought occurred to me. If a person falls freely, he will not feel his own weight. And he says this revelation startled him. And as he thought more about it over the next 8 years, the end result was the development of his general theory of relativity. So even though in one sense it's beyond the course, we want to get at least a little insight into what that is all about and see actually in a couple instances, well, one instance at least, the one we're going to talk about in this video, it gives us a result that is similar to the special theory of relativity, but different in a couple of key respects. And that is a time dilation effect due to gravity. So he talked about that if a person, as he says, if a person falls freely, he will not feel his own weight. And so the classic example of doing that, and Einstein himself used this, would be in an elevator. Okay, so let's imagine that here's just it's a thought experiment, sort of an elevator out there in the middle of space. If it's falling freely, or even just a real elevator, if you cut the cable, and there are no other safety mechanisms, as you fall freely, you will not feel your weight. If you drop a ball at that point, it will just stay there because you're all falling down toward the center of the Earth or down toward the surface of the Earth. So it'll be like gravity doesn't exist anymore. And Einstein started analyzing that situation a little bit more and noted also that if you, say for your elevator again, you attach a cable to it, right? And maybe there's a crane or something, again out in the middle of space, so somewhat fanciful here, but the idea is you have something where now you can lift the elevator up. In fact, you can accelerate it in an upward direction at some acceleration A. Again, just like we would do in a real elevator, as the elevator goes up, you feel that momentary push downward. You feel heavier. Okay, it's like gravity has actually increased. And so an acceleration upwards, if you're in the elevator, is therefore equivalent to a gravitational field. And this was essentially Einstein's happiest thought, and it came to be known as the equivalence principle. The equivalence principle, that essentially a gravitational field is equivalent to an accelerated frame of reference. Okay? That this person inside here, if they're walled off from everything, they could be in the most space for all they know. If the crane or the elevator or whatever, if the cable pulls up on them at an acceleration that's equivalent to the acceleration due to gravity, then it feels like gravity to them. They couldn't tell whether they were in the elevator just on the surface of the Earth, feeling gravity pulling them down, or they're actually out in the middle of space and some imaginary crane is actually pulling them at an acceleration such that they press down into the floor, as it were, and you feel that normal gravitational pull. So that's the equivalence principle. Gravitational field is equivalent to an accelerated frame of reference. And so you see that opened up some things for Einstein because he was interested in going beyond the special theory of relativity, which is only constant velocity, inertial frames of reference. And here was something that enabled him to perhaps, if he pursued this, to bring in accelerated frames of reference and also tie it into gravity as well. And so again, over the next 8 years, in a number of stops and starts and dead ends and so on and so forth, plus he was working on other things along the way, he was able to come up with this general theory of relativity. And the key thing here for analysis is that what the equivalence principle enables you to do is if you do an analysis involving acceleration, then the conclusions from that analysis also apply to a gravitational field, a situation where you just have a gravitational field occurring. And we want to do 2 examples of that. In this video, we're going to do the time dilation example. In the next video, we'll do the bending of light example. And so let's imagine a situation like this. So we're going to have an elevator here. And we'll have our 2 observers, or really 2 clocks. And so we'll put a clock at the top of the elevator, clock U for upper, and down here we'll have clock L for lower. And these clocks emit little pulses of light. So here's one, and we'll get some nice red pulses of light coming up here in that direction. And then up here, another little laser and pulses of light going down. And we'll have a detector here and there. Okay? And so the clock, each clock, and these are synchronized clocks, the identical clocks, and they emit these little pulses of light. That maybe they emit 10 pulses of light per 1 tick of each clock. Okay? Now another factor here is that we're going to assume any velocities involved are much less than the speed of light. So this example will have nothing at all to do with the special theory of relativity. We'll assume the velocities are low enough that we can ignore all relativistic effects, if they're very, very small compared to anything else going on here. So we've got the clock, so that means that the 2 clocks are in sync with each other, right? We don't have to worry about leading clock's lag and all that because any velocities involved are much less than c. And we're going to now put this into acceleration in an upward direction. So we're going to accelerate it in upward direction, but again, at very, very small velocities, just sort of ordinary everyday velocities, so we can ignore any special relativistic effects there. And so let's think about what happens then to, say, clock L down here, the observer at clock L. They will be observing these pulses of light coming down to their detector here. And meanwhile, their pulses go up to the detector for clock U. But because as these pulses are emitted here, of course, they're traveling along now. But while they're traveling, the elevator moves up slightly. It's accelerated up a little bit here, such that these, let's say, there are, again, 10 pulses per 10 pulses per tick of each clock. Okay, so clock L detector, though, because it's accelerated upward a little bit while these pulses are in motion, will collect more pulses per tick of its clock. It'll collect more of these pulses coming down because it's sort of moving up a little bit and sweeping through them a little bit faster because of the acceleration involved here. And so maybe instead of receiving 10 pulses, which it normally would do per tick of its clock, it receives 12 of these pulses of light coming down from the upper clock. So let's write that down. For clock L here, let's say it receives 12 pulses during 1 tick. 1 tick of its clock. Okay? So it receives 12 pulses coming down, whereas normally it would receive only 10. So what does that tell us then? It tells us that this clock, therefore, is running slower than this clock, okay? Because it's receiving 12 pulses during 1 tick. Well, they're both synchronized to do 10 pulses per tick, but now it's looking at the upper clock and it's getting 12 pulses per tick. So another way to look at it is the upper clock is running faster than it is. It's only doing 10 pulses. Well, it looks like the upper clock is doing 12 pulses in 1 tick. Therefore, the upper clock is running faster. You can also look at it the other way around if you want to do the perspective of the upper clock. It's accelerating, but it's accelerating away from the pulses coming up from the lower clock. And so as it gathers in those pulses at the detector, instead of maybe seeing 10 pulses coming in during 1 tick of its clock, 10 pulses from the lower clock, maybe it only receives 8 pulses during that 1 tick. So it's in terms of its clock, it's saying, oh, hey, I'm sending out 10 pulses per tick, everything's fine, but I'm only receiving 8 pulses per one of my ticks from clock L, and therefore it looks like the lower clock is running slower. So either way you analyze it, you come to the conclusion that if you have this acceleration involved, again, velocity is much less than the speed of light, no special relativity involved here, but just the fact that you have even a small acceleration, you'll find that the lower clock runs slower compared to the upper clock when they compare clocks. The lower clock sees the upper clock running faster, the upper clock sees the lower clock running slower in this case. And then you say, we've got the equivalence principle. Therefore, this situation also applies to a gravitational field. And I've got the acceleration going upwards, so if you put somebody in here standing in the elevator, if you make this equal to the acceleration due to gravity on Earth, then that person would feel a gravitational field. It would be like as a gravitational field, and Einstein would say, according to the equivalence principle, it's the same analysis either way. So the conclusion here is we did the analysis with an accelerated frame of reference and concluded that the upper clock runs a little faster than the lower clock, or the lower clock runs a little slower. In other words, lower down in a gravitational field, clocks are going to run slower than up high. Lower altitude, at a lower altitude in a gravitational field, like at the surface of the Earth, if one clock is at the surface of the Earth and one clock is up on an airliner or up in space on a satellite, this clock on the surface is going to run slower than the clock on the upper part, the higher altitude. And so this is gravitational time dilation. Is what we're talking about here. So not only do we have a time dilation effect at high velocities, special theory of relativity, when we're just in a gravitational field, there's a time dilation effect between lower clock and a clock higher up in the gravitational field. And they've actually done experiments with this. The physics building, they just sort of, from the basement to the top floor, they have two very accurate clocks, it's not quite set up like this with the pulses, but something similar to this. And you can actually see that the lower clock runs slower than the upper clock, even over just the height of a building. Again, if you have very accurate clocks involved. Another thing, we've actually mentioned this a couple times before, but the global positioning system, the GPS system, has to be designed to take this into account. And actually has to be designed to take into account the special theory of relativity and the general theory of relativity involving gravitation here. It turns out, if you do the analysis on the satellites that are involved in the global positioning system, they're moving at pretty high velocity compared to the Earth, and compared to just a reference point on the Earth. And therefore, it turns out if you do the analysis for the special theory of relativity, so special theory says that the clocks, since they're going faster, time dilation, right? If you observe the clock of a moving object that's going fast, you, the observer, say here on the surface of the Earth, and we watch the satellite going by overhead, or really the satellite might be stationary, but we're rotating on the Earth, however you want to look at it. We're at rest, satellite is moving, therefore we observe the satellite clock running more slowly, and it's about 7 microseconds slow per day is the effect. This is abbreviation for microsecond, millionths of a second. 7 millionths of a second slow per day. Gravitational time dilation, however, so the general theory of relativity, the general theory from gravitational time dilation, if you do the analysis there, remember the lower clock is going to run slower. The higher clock, in this case the satellite up there in space, is going to run faster. And so the satellite clock, from our perspective, runs about 43 microseconds fast per day. So there's sort of competing effects there. And you put them together and you can see that it's roughly, what is it here? 36 microseconds, something like that. It's in that range. I forgot the numbers quite right there. But 36, 37 microseconds when you do the analysis. Fast per day. And you might say, well, that's not a very big difference. If you're talking about millionths of a second, 38, 40 millionths of a second, whatever it is. But at the speed of light, Okay? As the signals go from ground to the satellites at the speed of light in about 30 to 40 microseconds travels 10 or 11 kilometers. Okay? What that means is, in designing the GPS system, if you don't take into account the special theory contribution and then the general theory contribution in the other direction, fast for the general theory time dilation, gravitational time dilation, and slowing down for the special theory of relativity. If you don't take both of those into account and get the numbers right there, your GPS system is going to drift by 10 or 11 kilometers per day. In other words, it's not going to be a very accurate system. So they actually had to design the system such that the clocks ran slow on the satellites. Okay? In other words, they had to run slow by 36, 37 microseconds, something like that, per day compared to a clock, if an identical clock at the ground there. And so by taking that into account, they were able to get a very accurate system. So again, that's Einstein's happiest thought or most fortunate thought of his life, depending on how you do the translation of the German. Occurred in 1907, developed it over the next several years into the general theory of relativity, or one key part of the general theory of relativity. And one of the consequences of that, again, is gravitational time dilation, that a clock in a gravitational field, lower down in a gravitational field, runs slower than a clock higher up in a gravitational field. In the last video, we introduced the idea of Einstein's happiest thought, as he termed it, and the equivalence principle that an accelerated frame of reference is equivalent to a gravitational field, and therefore you can do analyses of accelerated frames of reference and apply the results to the situation of a gravitational field. And we did that in a simple case to show gravitational time dilation, that clocks lower down in a gravitational field will actually run slower than clocks higher up in a gravitational field. And we mentioned the example of the GPS, Global Positioning System. In fact, actually, one slight correction here, I wrote down the wrong numbers. We talked about how the clocks on the satellites run slower due to special relativistic effects because they're going at a high velocity compared to the clocks on Earth. And so the difference there is about 7 microseconds. They run slower compared to an identical clock on Earth. But then you have the gravitational time dilation effect, so the clocks on the satellites higher up in the Earth's gravitational field will actually run faster. And I wrote down 43 microseconds. It's actually 45 microseconds if you want to be a little more precise about it. The conclusion was the same, however, that there was a correction factor of, in this case, actually 38 microseconds that need to be built into the system. In other words, they made the clocks of the satellites run slower by 38 microseconds a day than the clocks on the ground, just to make the whole system work correctly. So that's where we were with the equivalence principle. I wanted to do one more example with it, because it comes directly into the history of Einstein, as we'll see. And you may remember, if you read the profile of the young Einstein at the end, we talked a little bit about this. But it's the bending of light by gravity. So again, the equivalence principle says if we analyze something in an accelerated frame of reference, then the results should apply, so we've done things correctly, to the situation of a gravitational field. So here's the idea. We're going to do two perspectives on an elevator. The elevator operator perspective, sort of looking from the outside, and then the perspective of an elevator passenger inside. So maybe we'll have A for Alice here. So Alice will be so here's Alice. She'll be the elevator operator, and we'll put Bob in the elevator here. I won't draw him in yet because we need to do something over there. Don't want to mess that up too much. So here's the situation. Alice is the elevator operator. She's going to accelerate the elevator upwards, either via a crane or just the regular elevator mechanism. And also, there's a little hole you can see on the left side of the elevator. We're going to insert a beam of light, shine a beam of light there. So here comes the little beam of light going in there. Roughly sort of a messy beam, but there it comes in. So remember, this is Alice's perspective. And so she's going to insert that beam of light it's going to travel just straight across as far as she's concerned, horizontally, as the elevator, of course, is accelerating upward. The elevator is being raised here. So what does Alice see? We've got 3 snapshots, 1, 2, and 3. So in the first snapshot, she sees the pulse of light enter the elevator. In the second snapshot, a little bit later, the pulse of light, of course, is traveling across here. So here's the second snapshot. It's going to be at the same height, comparatively. So now the pulse of light is right about there. Let's move it up just slightly here. I made something like that. So I think that's pretty horizontal there. So again, compared to Alice, pulse of light is going across horizontally as the elevator is moving up. And then finally, in the third snapshot here, the pulse of light gets across to the other side and impacts right there on the wall of the elevator down low. Okay? So that's Alice's observation, the elevator operator perspective of just that pulse of light going through a hole in the elevator, hitting the other side. But of course, the elevator is accelerating upward, and therefore it's going to hit down there. Now, what about the passenger perspective? Say Bob inside here. Well, of course, he will see the light come in, and I didn't really say this is down here. It really doesn't matter. Bob, as far as he's concerned, remember, he's not moving. Okay, elevator is accelerating upward, but as far as he's concerned, it could just be a gravitational field. He could be just sitting on the earth in the elevator feeling the force of gravity, or he could actually be accelerating. But what is he going to see in terms of the light beam going across there? Well, they both have to agree that the light beam comes in the hole like that. So they're both going to see that. They can both take a little quick photograph there. They also both have to agree that the light beam hits down here at the bottom. Maybe it makes a little hole or something there, a little burn mark, perhaps if it's a laser beam. So they have to agree that. In snapshot number 3, they both have to agree this is where the light beam hits, right there. And in the middle picture, they both have to agree, if they could take a snapshot there, the light beam's sort of halfway from the top and the bottom. So something like this. And so look at the path of the light beam from the perspective of Bob, the elevator passenger here. Now, as we've drawn it, you could say maybe it just goes, straight down in a diagonal line. In actual fact, because the elevator is accelerating here, the effect sort of gets amplified as it's getting closer to the bottom there. And so the actual path will be a curved path, not just a straight line path. It'll go down something like that and hit there. In other words, if we took multiple snapshots here, a video of it, we'd see the path of the light from the perspective of Bob inside the elevator. The passenger would follow a curved path and hit on the wall there, whereas outside to Alice, the elevator operator, would just be going straight across, but hitting right there. So this is a very simple analysis, nothing very profound about it. It's just the elevator is accelerating. That's all that's going on here. It doesn't even have to be a very fast acceleration. So no special theory of relativity effects here. But the conclusion is, if the equivalence principle is true, that this is the analysis of an accelerated frame of reference. Therefore, this also applies to a gravitational field. And what that means is, in a gravitational field, that light will bend. Because we know, from the perspective of the elevator passenger, light definitely travels a curved path from their perspective. But again, as far as they're concerned, they could just be the elevator could be on the surface of the earth, not moving at all. They could just feel that gravitational field. So they don't know whether they're feeling acceleration upward or whether they're stationary on the surface of the earth and feeling just a gravitational field. In either case, they'll have to see light bend, follow a curved path. So in the presence of a sufficient gravitational field, light will bend. Actually, I should say, in the presence of any gravitational field, light will bend, but gravitational field on the surface of the earth is not really strong enough to get much effect here. If you actually analyze, as light goes across, very quickly, of course, from one side to the other of an elevator on the surface of the earth, the bending of light during that very short time period will be about less than half the nucleus of an atom in terms of the amount of bending it goes through. So essentially, we'll see it just go straight across. But And here's where it comes into play in terms of the history of the development of the general theory of relativity, which Einstein put the finishing touches on in 1915. And one of the results of that was the prediction that light would be bent under the influence of gravity. And it would require a fairly strong gravitational field. Turns out, if you look at starlight coming past the sun, okay, so we can observe a star out there just past the edge of the sun, that that light as it travels near the sun should be bent and reach us compared to if the sun wasn't there. Now, unfortunately, when the sun is out, obviously, we can't see the stars right next to the sun. But during a total eclipse, we can. And therefore, we can observe stars when the sun is away from them. You know, at night, different sun's gone, of course, on the other side of the Earth. So we observe a star, and then during an eclipse, if the sun is right next to that star, the light from that star should be bent when it reaches us. And so the observed position of the star should shift slightly compared to when the sun is there or the sun isn't there. And again, we can't observe that bending unless we have a total eclipse right at that instant to block out the light of the sun so we can actually see the stars. And so they had the idea to do this, these observations during an eclipse to see if light would actually bend a certain amount. In fact, the Newtonian theory of gravity also predicted a certain bending of light in that situation, but a different result than Einstein's theory did. You may remember about this time, 1914, 1915, World War I was going on in Europe. So what happened was early attempts, right about 1914, failed because of the outbreak of the war. But by the time the war ended, essentially 1917, 1918, there was another eclipse coming up in 1919 that was going to be able to be observed as a total eclipse, partly on the coast of Africa and across the Atlantic Ocean, and also partly in Brazil. And so the British mounted an expedition led by Arthur Eddington to see if this was actually true. So they sent one team to Brazil, they sent another team to the west coast of Africa. Unfortunately, the observations were pushing the limits of the portable equipment they were able to, because they actually had to go, of course, where the eclipse was. They couldn't just use a really nice observatory. Pushing the limits of the equipment they had, plus anytime you have an eclipse, there's also the danger of a cloudy day or whatever. And so they were up against some of that, but they did get enough data such that late in 1919, they the British announced that Einstein's theory was confirmed in this case. And it just caused a sensation because here was a world that very weary of war and the nationalistic fervor that presaged that and built up during the war. And so here was this British expedition confirming the work of a German scientist, okay, an enemy scientist to many people, overturning the work of Britain's greatest scientist, or maybe even the world's greatest scientist, Isaac Newton, up to that point. And the press caught wind of this a little bit, and it even came across the Atlantic to the United States. And the New York Times, after this meeting of the Royal Society of London, where it was announced, had these headlines. The first headline said, "Lights all askew in the heavens." In other words, things were a little weird there in the heavens. And then they had 5 sub-headlines in the style of the day. "Men of science more or less agog over results of eclipse observations. Einstein theory triumphs. Stars not where they seemed or were calculated to be, but nobody need worry. A book for 12 wise men. No more in all the world could comprehend it," said Einstein when his daring publishers accepted it. Now, most of that was just fiction. Okay, there were more than 12 wise men who could understand it, and there were no daring publishers involved, and so on and so forth. But men of science, and they were mainly men, were more or less agog over results of the eclipse observations that confirmed Einstein's general theory of relativity and the bending of light. It was still controversial, and in fact, even by this time, Einstein was recognized within the scientific world. And then after this, the eclipse expedition that confirmed his theory, this is when he became world famous and a scientific icon. He made a tour of the United States, was invited to tour to raise money for the campaign to develop a Jewish homeland in Palestine. And so he did that. And it was like, well, later on in the decade, Charles Lindbergh, the ticker tape parades, and even later on, years later, rock stars and astronauts and so on and so forth. So he became a celebrity at that point in the 1920s. He wasn't yet the scientific icon with the white, hair going all over the place and sort of the sad, wise expression, the sage-like expression. But he certainly was fast with a quip, and journalists loved him. And so from that point on, they were often calling him up to get his latest opinions on this, that, or the other, not only for scientific matters. So that's when he became world famous. And you may ask, well, what about the Nobel Prize? He actually had not won it at this point yet, which was causing some problems for the Nobel Prize Committee, who was making these decisions. The Nobel Prize at that time really was focused more on experimental results and discoveries, and the committee was dominated by experimentalists, and people still had some doubts about the special theory of relativity and certainly the general theory of relativity. Even though the Eclipse expedition confirmed the results, you could still question about the experimental analysis and reducing the data and the observations and so on and so forth. So it was fairly controversial. Einstein had been nominated for the Nobel Prize starting in 1910 and then almost every year after that. And then finally, in 1921 and 22, they had no physics prize awarded in 1921. And then in 1922, Einstein was world famous. People were wondering why the greatest scientist since Newton hadn't won the Nobel Prize yet. They actually ended up giving it to him for his discovery of the law of the photoelectric effect, one of his other 1905 miracle year papers, where you may remember he had the heuristic idea of treating light as a particle, essentially, and analyzing the photoelectric effect and some other things along with that. So they were able to do that, gave him the 1921 prize. Actually, in 1922, at the same time, they gave the 1922 prize to Niels Bohr, who was a pioneer in quantum mechanics and had built some of his quantum mechanical theories based on Einstein's work. So it was a nice way to solve that problem. But what's interesting is that in the prize citation, the Nobel Committee specifically accepted, not accepted as in AC, so not this type of accepted, so not that, but accepted the theory of relativity, whether the special theory or the general theory of relativity, from the prize. The idea perhaps was that maybe he'd get another one down the line when the theory of relativity, whether special or general, was a little more accepted, this type of accepted, and also perhaps confirmed a little bit more. All of that never happened. So he won the Nobel Prize, the 1921 Nobel Prize in Physics, specifically for the discovery of the law of the photoelectric effect, as the prize committee termed it, and also it said for his general services to theoretical physics. So you could include certainly his relativistic work in there as well.